And is share screen in progress? That's the question. Let's get it right. You'll be happy to know I'm finally getting rid of my old flip phone. I actually bought an iPhone and I'm setting it up. I would just wonder what in the world do people do if they lose their phone and then they can't get all their two-factor authentication. They're locked out of all their accounts and everything. What do people do? I'm not sure this two-factor authentication is a good idea.
I think Berkeley has, for your account, you have like backup codes. So if you lose your phone or something, as long as you like store them on your computer, they
Yeah.
have like 20 backup codes or something.
Yeah,
Like,
yeah, I understand because I just printed it out this morning on a page of them. Yeah, so I know what you're talking about. But this morning, in order to set up my two-factor authentication on my iPhone, I had to download an app on the new iPhone, and then Apple, in order to do the download, they wanted me to do two-factor authentication. And so they sent this to the trusted, what they thought was my trusted device or something, which God knows where it is because I didn't receive anything. So I felt like I was in an infinite loop of, two-factor authentications, which were failing, Anyway, I think I finally got it together. So now I'm with the rest of the world having to plug in my phone every night. Okay, so I'm going to go, there's a lot of stuff we covered last time. And I suspect it would be useful for you to kind of hear the highlights of it, to get something of a bit of a bird's eye view of what we did last time. So we can talk about it intelligently tonight. So I'm going to start with that. So this is kind of a big review of what we did with time-dependent perturbation theory, as quick as I can do it. So the Hamiltonian is H0 plus H1 as usual in perturbation theory. We go to the interaction picture, which means we strip off the time evolution due to the unperturbed part, the H0. That's carried out by U0 dagger, connecting us in a Schrodinger representation to the picture, to the interaction picture, and similarly for operators. Then working in the interaction picture, we develop so in the interaction picture, the idea is the evolution is now just due to H1 because the part due to H0 has been removed. So if H1 is small, then we can create a power series in H1. And hopefully that'll give us a workable solution. Well, that's the idea of the Dyson series. The Dyson series expresses the solution in the interaction picture in terms of the initial state plus a series of correction terms, each of which involves one higher power of the perturbing Hamiltonian. The first term is linear in it, second term is quadratic. They involve integrals, and in fact, the Dyson series is obtained by an integral equation, which is equivalent to the Schrodinger equation in the interaction picture, which has been iterated by substituting the left-hand side into the right-hand side over and over again to generate a series. And that's kind of where it comes from. Anyway, then we take the state in the interaction picture and we expand it as a linear combination of unperturbed eigenstates, which we call n. Here's the notation for that, is the H0 axon n brings out En. By the way, this initial state up here, we normally assume it's an eigenstate of H0. It's just a special case of n. The idea is I is a particular initial state and n is a variable final state. That's kind of the notation that's used here. But we expand the solution as a linear combination of these unperturbed eigenstates with coefficients Cn, which are functions of time. While solving for them, what you find is that the Cn's are actually transition amplitudes. That is to say, it's matrix elements between eigenstates of the unperturbed Hamiltonian of the time evolution operator. W is the time evolution operator in the interaction picture. So these are interaction picture amplitudes, these Cn's. Anyway, when you square them, you get the probabilities, the transition probabilities. As I say, call it P sub n, but it really means a transition from the initial state I to the final state n. That's what the P sub n is. All right, so anyway, that's one page of review from last time. Now then, to continue, we then get the Dyson series for the amplitudes, the CNs of T's, which we're particularly interested in them because you square them and you get the transition probability. See, so the CNs are what we want to compute. And writing them out on the Dyson series, the first term is a Kronecker delta because at t equals 0, all the probability is in the initial state. And then there's first order, second order, et cetera, correction terms. Now I've just written out the first order correction term here. It's an integral over time of a matrix element of the perturbing Hamiltonian in the interaction picture. But if we convert it to the Schrodinger picture and assume that the Schrodinger Hamiltonian H1 is independent of time, then that matrix element, which is right here, can be taken out of the integral. And what's left is an elementary integral. And if you do it, you get these sine and exponential functions times this matrix element. Frequency omega ni that appears here is what I call the Einstein frequency connecting the initial and final states. The idea is you start in an initial state of the unperturbed Hamiltonian, it has some energy, you end up in a final state n, and it has possibly a different energy. If they're not the same, then there was a change in the energy in the transition, and that's what this omega ni measures. It measures in some sense the lack of energy conservation during the transition process. All right, so you get these time-dependent factors here, and if you square them, square the amplitude to get the probability, well, here's the probability is the square of the amplitude written out as a power series. But if we assume the final state is not the same as the initial state, then the Kronecker delta goes away. And if we work just to first order, then the higher order terms go away. And so with those understandings, then the probability is just the square of the first order amplitude like this. And if you just square the sine function stuff, the phase factor goes away. The answer can be written like this. There's a time-dependent factor times the square of the matrix element you see up there. This time-dependent factor is written in a certain way in terms of this function capital delta of the Einstein frequency, and it's defined here. The sine squared omega t over 2 divided by omega squared just came from squaring that time-dependent factor up there. But we write it as pi over 2t times delta t of omega, because if we do that, then in the limit that t goes to infinity, capital delta of t turns into a Dirac delta function. This is, it's not hard to see that this Dirac delta function is responsible for energy conservation, because when the Einstein frequency goes to 0, it means the final energy is equal to the initial energy. That doesn't mean the final state is equal to the initial state, because in the applications we have, I mean, for example, in a scattering, the outgoing state's got the same energy as the incoming state, but they certainly aren't the same states. But in any case, we're going to get energy conservation when this omega parameter is equal to 0, and that's what this delta function will do. But it only appears in the limit that t goes to infinity, and for finite t, there's some spread in energies in the final state, so there's some violation of conservation of energy over finite times. This is all related to the time energy uncertainty principle. Okay, so that's kind of the formalism of time-dependent perturbation theory, worked up, run over really quickly. We then made an application to potential scattering. We used a certain model. The model was we have a potential, which we call U of R, which could be lumpy, doesn't have to be rotationally invariant. We send in a plane wave with an initial wave vector ki, meaning k initial. And we want to analyze, so this is our initial state, and we want to analyze transitions to other plane wave states, which are eigenstates of the H0, which here is the free particle Hamiltonian, but with different k values. So they represent scattered waves going out in different directions. The formalism we developed, however, requires discrete states. That's how I was writing it down on the previous page. And in a scattering problem like this, the initial and final states are in the continuous unbound spectrum. So we fix that by going to box normalization. We put everything in a box. Excuse me. We divide the universe into boxes, all of them identical, and we require that everything be periodic in the boxes, including not only the potential, but also the wave functions, etc. And then when we're done, we take the limit of the volume of the box, which is the square, which is the cube of the length of the side goes to infinity. So anyway, then we end up dealing with a discrete set of plane wave states. And here's some of the basic formulas for them. They're normalized over the volume of the box, otherwise it's a plane wave. The K vectors take on discrete values corresponding to a lattice of K points in K space. It's given by an integer vector times this 2 pi over L. And with this normalization, these satisfy Kronecker delta orthonormality relations. To apply our general formulas for time-dependent perturbation theory, we need to make some changes in notation. The initial state I in the general notation goes over to Ki for the initial wave vector. The variable final state n, would just call it K like this, but we're going to be assuming that the real scattering takes place so that K is not equal to Ki. And that means that we're talking about that Kronecker delta term will go away, you see. I mean, if you're going to have real scattering, the final wave vector has to be different from the initial one. All right. Anyway, then we do that. Then we plug in the formula for the probability in first order perturbation theory. And it's got these time-dependent factors here with this delta function that's going to conserve energy times the square of the matrix element, which now looks like this. And as I say, this is for K not equal to Ki. What we call omega ni in the general formalism is the difference between the difference in energies between the initial and final states divided by h bar. So for this problem where these states are free particles, you get this expression, it's K squared minus K initial squared times h bar over 2m. And that's what needs to go in here into this delta T of omega. Okay, so that's the transcription of the formalism from the time-dependent perturbation theory. Now, to get a cross section, we need to start thinking about detectors and counting rates and so on. So let's have a detector, let's call it D here, and let's draw a unit vector, which I call n hat final, pointing from the origin of the coordinates. The potential energy is out here somewhere. You see the scatterer is there. The unit vector pointing from the scatterer towards the detector, like that. And then we draw the same unit vector over in K space with a small cone around it. The idea of the cone is it's the cone that which is subtended by the area entrance aperture of the detector. But in any case, we draw a small cone around this direction in final, and this gives us imagine K space filled with lattice points. It gives us a set of states, i.e. lattice points inside this cone, and we want to sum over them. We want to sum over all K that's in the cone of the probability of as a function of time of having the system in those corresponding plane waves. That's just a way of saying we're looking at waves that are going out in the directions that lie inside that cone. Okay, if we get that sum, if we can calculate that sum, then from that we get the differential cross section, which is just outlined here. The differential cross section is the transition rate per unit. Well, this is differential cross section, the cross section per unit solid angle. This is equal to the transition rate per unit solid angle, which I write as dw d omega divided by the incident flux. That's just the definition of a cross section, or it's one way to define it. It's the counting rate divided by the incident flux. As far as dw d omega is concerned, that's the differential counting rate, the counting rate per unit solid angle. That's equal to the probability of being inside the cone divided by the time. That gives us the rate divided by the solid angle. That's just what that means. And this sum here is what I was referring to up above. So you put this all together, you're going to have to take the limit where the volume goes to infinity. That turns this sum into an integral. When you do the integral, that capital delta function take time long enough to turn it into a Dirac delta function allows you to do the integral. That gives you energy conservation. There's a lot of details in this, but it's rather complicated, but when you put the pieces together, it all works. And you end up finally, when the smoke clears, with an expression for the differential cross section. And I think that's where we ended up last time. The cross section is expressed in terms of the square of the Fourier transform of the potential evaluated K minus Ki. That's to say the final K minus the initial K. This is also equivalent to what's called the first Born approximation. We'll say more about the Born series later on, and you'll get an idea of what second and higher order Born approximations are. The utility of K here is defined by this formula. This is just I write it down just to be clear about the normalization of the Fourier transform. It's got the factor of 2 pi to the 3/2 in here. Otherwise, it's just the Fourier transform of the potential, in which in this formula, the conjugate variable is called Q. Q is identified here with K minus Ki. By the way, h bar k is a momentum, so multiplying by h bar k minus ki is the final momentum minus the initial momentum. And this is this shows you that in the first Born approximation, the differential cross-section is a function of what you call the momentum transfer. This is an interesting feature of the first Born approximation. And it generalizes to relativistic scattering theory. In relativistic theory, you end up with a 4 momentum transfer. It ends up with the Lorentz square of the 4 momentum transfer, as you'll find out if you take a course in relativistic quantum field theory. But anyway, at the non-relativistic level, it turns into the 3 momentum. This doesn't hold a higher order Born approximation. It's not an exact result in scattering theory. It's just at lowest order, but it's an interesting result. So there's a lot of attention given to momentum transfer in scattering theory. Okay, I think that takes us up to where we ended up at the end of the hour last time. So let me pause and ask if there's any questions about this. I'm trying to give an overview of the principal features of what we did last time. Any questions? All right. If not, understand then that there are 2 aspects of what we did. We worked out the general formalism for time-dependent perturbation theory, and then we applied it to scattering theory, which involves some trickery in putting things in boxes with periodic boundary conditions, ultimately taking limits. We have this issue about the approximate delta function turning into an exact delta function. This sum over the cone, when you go to the infinite volume limit, turns into an integral. It's really an integral over k space. And the radial part of that integral dk, which goes from 0 to infinity, there's going to be this delta sub t of omega under there. And as t gets large, this is going to turn into something which is proportional to delta of k minus k initial, which will allow the radial integral to be done. But there's a question about how long t has to get for this replacement to be made. And I want to say a few words about that, because I think this is probably one of the most obscure aspects of this formalism, the part that may be the least clear about what's been done. But all right. So in evaluating this final result, I did replace this delta function. So now the question is, how long do you have? We don't really take t goes to infinity. How long do you really have to take t to get a delta function here, which allows you to do this integral? So I'd like to explain some things about this model of scattering theory. If I can go back to this picture here, this scattering theory calculation is done in the first place as an example of time-dependent perturbation theory, number 1. Number 2, it gives us a real result, namely the first Born approximation that we can analyze from various directions, and that's what we're going to do in the coming lectures. However, the manner in which the calculation is carried out has a number of defects, a number of shortcomings, and I'd like to point out at least a couple of them to you. The shortcomings have to do with basically the mathematical model that we're using for this problem. So the picture here shows you the idea is we imagine an initial state in which there is a plane wave. That was our initial state. It was an eigenstate of the free particle Hamiltonian. So it's a plane wave, fills up all of space, and it has a definite wave vector, which we'll call k initial. And so then that's how it is at t equals 0. And then for positive times, that wave starts to scatter and we start to get contributions or amplitude inside other waves that are in different directions. Those are the scattered waves. This is the layout, the basic idea of this approach to scattering theory. Well, one of the things I'd like to point out, if it's not obvious already, is that this is a rather artificial mathematical model for scattering for a number of reasons, but probably the most important one has to do with the fact that at t equals 0, you've got an exact free particle solution filling up all of space. Now, if there were, and that's unrealistic for a lot of reasons. Now, if there was some way that you could switch the potential on, turn a switch and click, it would be on at t equals 0, whereas for negative times, there was no potential at all. Then you could do this because you'd set up a plane wave that would be involved just sending in a beam of particles of a constant momentum. setting that up, to good approximation, you can do that in a limited region of space. Beams do that all the time. And then you switch on the potential, and then the scattering starts. But we don't normally have the ability to just switch on our potential abruptly at t=0. Normally the potential is just sitting there. So if the potential has been there for forever, then there's no way to get a plane wave that fills up all of space with a k vector exactly the ki everywhere, including in the region of space occupied by the potential. The reason is that in a sense, the wave vectors have the wrong wave vector down inside where the potential is. If you had particles coming in from infinity asymptotically with a fixed momentum, when they enter the region where the potential is active, they will start to bend. Their energy will change and their momentum will change. Their direction will change. Their trajectories will deviate from straight lines. But that's not what we have at t=0. We've got all these particles have their asymptotic momentum. It's as if they didn't fall into potential well at all. Their directions didn't change at all. So what's wrong with this initial state is that, in a sense, the particles which are in the region occupied by the potential have the wrong momentum. It's an artificiality of this initial condition, which, as I say, would be near impossible to establish in practice. But you can think about it nonetheless. So it's kind of like, so you'll understand the situation perfectly well if you just think about it classically. Classically, this plane wave corresponds to filling space with particles that are all a beam of particles that all have the same momentum. You know, to some approximation, you can do that. But the problem is that if there's a potential there, the particles that are down where the potential is, they have the wrong momentum. There's no way to get particles into that potential well without sending them in. And if they do, they're going to accelerate. So they have the wrong momentum. In fact, they might have a momentum that's too small to even escape from the potential well. Assuming it is a well, it could be a potential barrier. But if it's a well, they might well have a momentum that's too small to escape. And if so, they'll never escape. They'll be trapped in there. This is, of course, an analog of a bound state in quantum mechanics. On the other hand, they might have enough energy to escape. And if they do, they're going to get out once we turn on time and let them flow. They'll get out and they'll go off in some direction. But when they do, they're going to escape and go out to infinity, and they're going to have the wrong energy because they took them energy to get out of the well. So we won't have energy conservation. In other words, all the outgoing particles won't have the same energy as the incoming particles. So these are all artificialities of the initial conditions. But perhaps you can see that if you're willing to wait a little while, what's going to happen is that the bad particles will get either trapped and stay there forever, in which case we can ignore them, or else they're going to leave. And if they leave, they may have the wrong momentum, but they'll travel away in some kind of a front of bad particles that will radiate away from the scatterer. Meanwhile, new particles will come in from infinity. They will bend in the potential correctly and get scattered correctly. So this front of bad particles will be followed up by a what will ultimately turn into a steady state of properly scattered particles. So this means that if you wait long enough, proportionally, the bad particles, as part of the initial conditions, they count less and less in terms of the fraction of particles that are getting scattered. And in the limit that t goes to infinity, they don't account at all. They don't count at all for the scattering. So this is a way of saying that these initial conditions give rise to non-physical transients at small times. And this is related to this fact that this delta function isn't really a delta function at small times. Now, I don't want to belabor this too much, but the notes that I've handed out go into this in more detail than I'm going to right now. But the moral of the story of the analysis is that the amount of time you need to wait for this approximate delta function to be replaced by an exact delta function, so as to make negligible error in doing the integral against this integrand, in fact, is the amount of time that it takes these bad particles to flush out of the potential, the region where the potential is active, and then get on their way. In other words, it's really the transience of the artificialities and initial conditions. Well, okay, so I don't want to beat this too much, this problem too much. But this does point to the fact that this is a fairly ad hoc approach to scattering theory. It's probably the same one you saw in your undergraduate courses. But it points to the fact that there are reasons for developing better approaches to scattering theory, and we will do some of that. I want to make one more point also about this application of time-dependent perturbation theory. As I indicated, this gives you essentially a power Dyson series, gives you a power series expansion in the perturbation. Well, our unperturbed Hamiltonian is the kinetic energy. So if expanding in powers of the perturbation is going to work, then in some sense, the perturbation needs to be small compared to the kinetic energy. This is a way of saying that this approximation that we're developing here is called the Born approximation. The Born approximation, we've only got the first Born term here, but the idea is the Born or the Dyson series are really equivalent. They're different versions of the same thing, really. Both of them are power series expansions in the perturbing Hamiltonian. So they're going to work if H1 is small compared to H0 in some sense. Well, without going into rigorous details, the intuition is simply this, is that you want the kinetic energy from the kinetic energy term, the H0 term, to be large compared to the energies that are involved in the potential. This is a way of saying that the Born approximation is a high energy approximation. It's valid when the particles kind of blast their way through the potential without being deflected very much. So if you learn nothing else about conditions of validity of the Born approximation, you should remember at least that it applies at high energy and understand the reason why. It's actually not hard to see just by writing down the potential like that. All right, the Born approximation is a high energy approximation. All right. Okay, so that concludes my review, rather lengthy review of what we did last time. And what I'd like to do, starting with new material tonight, is to play some games with this cross section and learn some things about it. Are there any questions about what I've done so far? I used almost half an hour to review what we did last time. Any questions about this before we go on? All right, then. Then the first thing I'd like to do tonight is just to examine some cases of this first Born approximation, the potential, and just learn some things about scattering. So to begin with, let's talk about scattering by an electrostatic potential. So let's suppose we've got beam particles that have a charge. Let's call QB the beam charge. By that I mean the charge on the beam particles, the beam particle charge. If that's the case, then the potential that we're using here, which I'm calling U of R, is equal to the beam charge times the electrostatic potential, which I'll call capital phi of R. And let's suppose the target is given by a charge distribution rho of x. I'm using R here tonight instead of x, so let's call it rho of R, a charge distribution. So we're scattering a charged particle off of a distributed charge. That's the idea. Example of this might be scattering a charged particle by an atom. High energy physicists worry about this all the time because they have to deal with usually relativistic particles that are penetrating matter, and they want to know how far do they penetrate. Of course, other people worry about that too. The penetration of radiation, penetration of matter by radiation of charged particles. So for that, you need to understand how an individual charged particle scatters off of an atom, which is a distributed charge distribution. Another example that's worth mentioning is the classic experiments that were carried out in the 1960s and on into the 70s of scattering of electrons on nucleons, protons and neutrons. These were relativistic electrons carried. These experiments are carried out at Stanford that had the electron accelerator. And the point of that was to use electrons as probes of the internal structure of the nucleons. And the result of that experimental work was to discover or to show that the nucleons, protons and neutrons anyway, are comprised of three constituent particles, which we now call quarks. So it was a confirmation of the quark theory, the QCD theory that was developing at that time. It's an important series of experiments. In any case, let's just say there's a number of applications for scattering of charged particles off of various kinds of charge distributions. If you were going to do this, let's say for a neutron, you're going to be interested to know what is the charge distribution inside the neutron? How is it distributed? Is it uniform, spherically symmetric, whatever, you know? All right. So let's just say the target's described by a charge density rho. Now we can put these things together by using the Poisson equation that del squared phi is equal to minus 4 pi rho, like this. And you'll recall that in the cross section, it's expressed in terms of the Fourier transform of the potential energy, which is what I'm calling U tilde of Q. So to get U tilde of Q, we need the Fourier transform of the scalar potential. That's most conveniently obtained by Fourier transforming the Poisson equation. I'm using Q here as the variable conjugate to position and doing the Fourier transform. If we do that, then the Laplacian operator in real space turns into minus Q squared in Q space. So the Poisson equation can be written as minus Q squared times phi tilde is equal to minus 4 pi times rho tilde, where the tilde is understood to be evaluated as a function of Q on both sides as well, other side as well. That. So plugging this in, then we get U tilde of Q. Well, I can divide by Q squared here, change the sign here and divide by Q squared. I get phi tilde multiplied by QB. So I get U tilde of Q is equal to QB times 4 pi divided by Q squared, lowercase q squared, times rho tilde of Q, like so, thereby expressing the Fourier transform of the potential in terms of the Fourier transform of the charge density of the target. Now, in this business, people define a quantity they call f of q. They may use different symbols for it, but they define it this way. And f of q is just basically the Fourier transform of the I'm calling it R here, Fourier transform of the charge density, q dot r, like this, rho of q, excuse me, rho of r here, rho of r. And except for the factors of 2 pi and so on, this is actually the same thing as rho tilde of q. In fact, this is equal to 2 pi to the 3/2 times rho tilde of q. But to show you how this is done conventionally, people work with f of q instead of rho tilde of q. This is called the form factor. The form factor is basically, in this electrostatic model, it's a form factor is basically the Fourier transform of the charge. So the solving for expressing U tilde of q in terms of the form factor, this becomes QB times 4 pi over q squared times the form factor f of q divided by 2 pi to the 3/2. There's various factors of 2 pi that appear here, like so. So let me box this because this is our U tilde of q. And if I now put this together in the differential cross section, d sigma d omega then is equal to, in the firstborn approximation, here it is. I just need these prefactors times the square of u and identify q with k minus ki. So this is going to give me d sigma d omega is equal to, it's going to be 2 pi m squared over h bar to the 4th times the square of this thing, qb squared, times 16 pi squared divided by q to the 4th times f absolute value of f of q, the form factor squared. The form factor is a complex factor in general, divided by 2 pi cubed, which is 8 pi cubed, like this. And if I clean this up some, I get 16 times 2, so I get 4 m squared qb squared, form factor squared f of q squared, divided by h bar to the 4th times q to the 4th. Okay, so that's d sigma d omega then in terms of the form factor and the q value, where the q here is the same thing as the final k minus the initial k. And by the way, it gets multiplied by h bar. H bar q then becomes the difference between the final and initial momenta. So let me write it that way, P minus P initial. You can picture the scattering process like this: is here's the initial PPI like so. The scattered particle goes off in the final P, which is, we're just writing it as P, and there's a scattering angle theta in between. And these two momenta have equal magnitudes because we've already been through conservation of energy and deriving the cross section. All right, so this is the basic picture here. So you can see that if I take this H bar, if I take this H bar Q and square it to give H bar squared Q squared, it's the square of P minus PI, which is therefore P squared minus twice P dotted into PI plus PI squared. Let me tear this off to create some space here. So, hope you can see this. But P and PI, as I just mentioned, have the same magnitude, and P dot PI is a magnitude times the cosine of the theta in between. So this is the same thing as twice magnitude of P squared times 1 minus cosine theta. And by trigonometric identity, it's the same thing as 4P squared times sine squared of theta over 2. And so the result is that H bar to the fourth times P to the fourth is the square of that. Oh, and by the way, P squared is equal to 2me, where E is the energy of the particle. So H bar to the fourth, P to the fourth, squaring that, I get 6 is equal to 64 m squared times E squared times sine fourth theta over 2. And if I plug that into my formula up above for the cross section, then you get some cancellations, and m squareds cancel. Let's do it right here. We get d sigma d omega is equal to, I'm just doing the algebra here, is equal to the 4 and the 64 combined to give you a 16. The m squareds cancel. I get qb squared divided by 16e squared times sine 4 theta over 2 times the square of the form factor f of q vector absolute value squared. So let me box that, because this is the same formula really is up above, but I've explicitly expressed q in terms of the initial and final states in the scattering process. All right. So this is the first Born approximation for the scattering from of a charged particle by distributed charge. All right. Now, the most obvious application of this would be to apply it to the case of a point charge as a scatterer. If we have a point charge, then the form factor f of q, so point charge is one in which the charge density rho of r is equal to, let's call it the target charge qt times the Dirac delta function, like this. So this is the point target. So doing the Fourier transform of that, this just turns into qt. It just becomes a constant. Fourier transform of the delta function is 1. And so in that case, what we get is d sigma d omega is equal to q beam squared times q target squared divided by 16e squared times sine 4 theta over 2. And you may recognize this as the Rutherford cross section. Okay. So isn't this nice? We've derived the Rutherford cross section by using time-dependent perturbation theory in quantum mechanics. Now, there's a little problem with this that I have to tell you about. This result is one of the greatest flukes in all of physics. I haven't examined in this theory the conditions of validity of the various steps that we've made, except to mention that it's a high energy theory. It's a valid, generally the Born approximation only at high energy scattering. By the way, later on, we'll talk about other techniques that allow us to access low energy scattering. But this is what we have for now. But except for that, I haven't gone into any quantitative measure of the conditions of validity on the result. And I'm not going to either, but I'll just tell you that if you go through that, what you find is that those conditions of validity are not met in this derivation with a Coulomb potential. Now, in general, for some potential, the conditions of validity are met. Whether they're met or not depends on the incident momentum. As I say, for high momentum incident particles, the approximation works better. But this one is so bad that it doesn't. The conditions of validity aren't met for any momentum, no matter how high it is. So, in other words, number one, how do we get the Rutherford cross section when the derivation is not justifiable? Number two, the Rutherford cross section, the way it's usually derived, is classical. We did a quantum derivation. Does that mean the classical cross section is different? If so, why? And why did we get the right answer? Okay, so there's all these questions come up. Well, I'll try to clarify the situation a little bit. In the first place, it is possible to calculate the scattering cross section for the scattering of two charged particles in quantum mechanics and do it exactly without any approximation at all. The way you do it is you basically solve the hydrogen atom for positive energies. You go back and give a radial wave equation, you solve it, it turns out it's Laguerre polynomials. It's not actually not Laguerre polynomials, it's hypergeometric functions for the positive energy solutions. And then you put them together, you can do a lot of work, and you can find the cross section, the exact cross section. And lo and behold, it turns out to be the Rutherford cross section. In other words, this is the right answer, even done not by perturbation theory, but by doing it exactly right in non-relativistic quantum mechanics. Now, if the conditions of validity of the Born approximation are not met, then why did we get the right answer? And does that mean that all the higher order corrections to the Born approximation are zero somehow? Okay, well, here's the story. Is that there is an object in scattering theory called the scattering amplitude. It's usually denoted f of theta and phi. It's a complex number, but it turns out that when you square it, you get the differential cross section. And if I have time tonight, I'll go into that and I'll explain that to you. It turns out that for the Coulomb scattering, the Born approximation gets the magnitude of that complex scattering amplitude exactly correct, sort of by an accident. But the phase is utterly wrong, completely wrong phase. That's where the error occurs. But when you square it, the phase disappears and you don't see it in the cross section. So roughly speaking, that's why, a wrong technique gave you the right answer. However, if you want to talk about the scattering of two identical particles, then there are what you call exchange amplitudes of the same type that we saw in talking about atoms when we had identical electrons. And those exchange amplitudes involve interference between scattering. You have more than one type of an F. You have an F direct and an F exchange. And there the phases do matter. And what you find in that case is that in Coulomb scattering of identical particles, like electron-electron scattering, for example, you get interference terms. And those interference terms calculated by the Born approximation are completely wrong. So in other words, it fails for identical particles, but just because phases cancel it, it happens to work for distinguishable particles. Okay, so that's kind of a complicated situation. All right, now, does this mean that the derivation I just went through, the form factors and everything, is useless? The answer is no, because this is not a valid derivation of Rutherford. But if the particle is not a point particle, so you have a different form factor, then there usually are conditions under which the derivation is valid and is useful. So that's one reason for presenting this. In particular, let me say some things about this. Maybe not too much, because maybe I'll turn it into a homework problem. But you can see by comparing these two formulas that the cross section in the case of a distributed target, the target in which the charge is distributed, involves the form factor, where if it's a point charge, there is no form, or the form factor was constant. Therefore, the form factor is a kind of a fudge factor, which converts the Rutherford cross section into the actual one you get when there's a distribution of charge. That's one way of thinking about it. That's why they call it a form factor. Now, the reason that the Rutherford cross section fails, or the in the application of the why the method is not valid for the Rutherford cross section is because the Coulomb potential has a long range tail, and that's manifested by, dies off slowly, only as 1 over r, and that's manifested by the sine 4 theta over 2 in the denominator, which means that the cross section diverges at small angles. Thus, there's a large probability of small angle scattering. It obviously comes from the very large distances away from the center, where you still get some significant scattering because the potential dies off only so slowly. So this divergence in the denominator is symptomatic of the pathology of the Coulomb potential as far as this problem is concerned. But you can see that with a form factor in here, this f of q has a possibility of canceling out some of that. Well, this was actually q to the 4th down here. The f of the q squared is a possibility of canceling out some of that denominator. And it turns out that if the total charge of the target is 0, so that there is no Coulomb tail, and that cancels out 2 powers of the q to the 4th that's down here. If in addition there's no dipole moment, then it cancels out an additional 2 powers and therefore eliminates the q to the 4th singularity. If that's the case, you end up with a differential cross section which is now well behaved and at all values of q. So these are features that come from looking at the form factor in more detail. All right, I think I'm going to stop talking about that because I spent much more time on it than I wanted to. Yes, question.
Is there a good physical reason why the magnitude should be exactly right, even despite all the problems?
I don't know. There may be. Why did the magnitude come out right and the phase totally wrong? I have no answer to that question.
Okay.
But I mean, it's a strange situation, and there are higher order Born corrections, right? I mean, they're there. Now they're essentially meaningless because the series is not even the first term converges. So the first term isn't even close if you include the phase. But there are higher order corrections as well. Anyway, there's higher order terms in the Born series. All right. So if you want to see how to derive the Rutherford cross section and quantum scattering and doing it right by solving the unbound solutions to the hydrogen atom, you can find that presented in Schiff's book on quantum mechanics, which goes through the calculation. Schiff was a student of Robert Oppenheimer's. There's a story about that. Okay, later on became chairman of the department at Stanford. All right. Okay, so that's all I want to say about this application of time-dependent perturbation theory to scattering theory. I'd now like to turn to another approach to scattering theory, which is to basically solve the Schrodinger equation for positive energies. So we're going to be interested in solving the usual Schrodinger equation. We'll do it in 3D, h bar squared over 2m, and just write it out. We have a potential, I'll call it potential V now, I'll call it V of x psi is equal to E psi of x. And this is the same old Schrodinger equation we've been solving before in this course, except tonight we're interested in positive energy solutions, or greater than or equal to 0 energy solutions. So the potential we will assume is a scattering potential, meaning it dies off rapidly enough to be interesting with distance. So at large distances, the particles are essentially free. We assume that. The positive energy solutions, therefore, are solutions that extend out to infinity. They're not normalizable, and they're a part of a continuous spectrum. So we're dealing now for the first time really in this course with a continuous spectrum in a serious way, a serious non-trivial way. Those are the solutions that we want to find. Now, to be proper scattering solutions, however, they have to satisfy the right boundary conditions at infinity. They can't just be any old positive energy solutions. So we need to take care of boundary conditions. So now let me talk about that, boundary conditions. Let's draw the picture that we want to think of here in terms of the scattering problem. We've got coordinates x, y, and z. We have a potential which is allowed to be lumpy. It doesn't have to be rotationally invariant. Here's v of x like so. And as before, we send in some plane wave like this with some initial momentum, which I'll just call it k here, not ki. I'll just call it k for this part. like so. And you know the picture of what's going to happen. You're going to get scattered waves that radiate outwards like so. You have waves traveling outwards like so in the scattered waves. So unlike in the calculation we just went through in time-dependent perturbation theory, which was a time-dependent problem, we started out with this initial plane wave, and then we turned on time, watched how it evolved. What we're interested in here now is a stationary state, which is to say an eigenstate, an unbound eigenstate of the Schrodinger equation with positive energy. As long as I'm talking about stationary states, let's think about the classical scattering. You can imagine a situation in classical scattering where we turn on a beam. Let's say the beam is wide enough to encompass the width of the range of the potential. And we've done a good job of making the beam particles all have the same momentum. So they're going to come in. We have to switch on the beam at some time. There's going to be a front. The beam's going to come in, interact with the scatterer. Scattered particles will radiate outwards. And if we wait long enough, we get a steady state. Well, not a steady state everywhere in space because there's a front of initial particles that keeps on traveling further and further out. But if we sit at some point in space and wait, that front will pass us. And then what's left over is a steady stream of particles passing by us like that. And that's what represents the steady state. So the region of space which is occupied by the steady state grows with time, and we can imagine an idealization in which it turned on, the beam turned on at t equals minus infinity, and we wait forever into the future, and now all of space is filled with a steady state. Now, I think that's easy to visualize, but this is just a classical steady state. However, in quantum mechanics, an energy eigenstate is called a stationary state, not because the wave function is stationary, because it isn't. It has a time dependence, but the probability and the current are steady. They're independent of time, and so this suggests, correctly as it turns out, that in quantum mechanics there is a steady state that can be associated with the same parameters as the classical steady state. The classical steady state is determined by the incident momentum and nothing else. That's all. Well, by the incident momentum includes the direction. So that's all you need. This K vector here determines everything for the classical steady state. This suggests that that there is a unique solution of the quantum Schrodinger equation in which there's an incident wave with a definite K vector and is an energy eigenfunction of the Schrodinger equation everywhere in space. This turns out to be true. These energy eigenstates are parameterized by the incident K vector. And the way to prove uniqueness is to use the theory of integral equations, which I don't want to go into right now, but let's just say it can be done. So this intuition that you get from the classical picture is actually correct. So what this means, then, to go back to the quantum mechanics, is we want to solve the Schrodinger equation with a positive energy, and we want to have the right boundary conditions, the boundary conditions involving an incident plane wave coming in from large distances from some direction. The K vector determines the direction, you see. And then we want to have scattered waves that are radiating outward from the scatterer. Okay. Now that leads to a decomposition of the wave function. Let's write psi of x here as the exact solution that we're interested in. And this should have the form of an incident wave, which I'll write as e to the I k dot x. This is the incident wave. And then what's left over, I'll call the scattered wave. So this equation defines the scattered wave. This is a definition of the scattered wave. It's the exact solution minus the incident wave is a scattered wave. However, we're going to require boundary conditions on the scattered wave, which is this, which is we require that as the radius goes to infinity, the scattered wave becomes asymptotically equal to e to the I k r over r times a function f of theta and phi. Certain functional form for the scattered wave in the asymptotic region, large distances. This little tilde here, what that means is that the right-hand side is an asymptotic form of the left-hand side. Or to put it another way, is that there are correction terms to this. This is not the exact scattered wave, but the correction terms are terms that go to zero as r goes to infinity more rapidly than the term which I've given you. So the scattered wave is equal to this term plus other stuff that dies off more rapidly than what you see. So that's going to be the meaning of the tilde in my lectures on this topic. All right. Now, this e to the I, why do we require this? Why do we require that the scattered wave have this asymptotic form? So let me explain it. In the first place, the e to the ikr, if we were to incorporate the time dependence, excuse me, e to the ikr, the time dependence would be minus iet over h bar, like so, if you put the time dependence in it. And this is an outgoing wave. This is a wave which is radiating outwards. So that's what the e to the ikr does for us. It gives us a radially at the large distance, it's a spherical wave. You see it's radiating in the radial direction. That's what this is. Now, why does it fall off as 1 over r? The reason for that is essentially conservation of probability or particles. The probability density, rho, is, of course, goes like psi squared. So as far as the scattered wave is concerned, this would mean it goes 1 over r squared. Well, in terms of its r, it has an angle dependence, but in terms of its r dependence, it goes as 1 over r squared. Now, why is that reasonable? It's because the area of the sphere, if you think it's larger and larger spheres in the asymptotic region, as they get larger and larger, the area grows as r squared. If the probability density falls off as 1 over r squared, then the amount of probability in a small spherical shell remains constant as that shell expands outwards. You see, at large distances, it's evolving as a free particle. So, a shell of a fixed thickness just propagates outwards into a larger shell of the same thickness. So this 1 over r here is related to probability conservation. And then finally, the f of theta and phi, what that does is it allows for an angular dependence for the scattered wave. We know that there's going to be an angular dependence in general. Sometimes there's more particles scattered in one direction than another. So this is a hand wavy intuitive argument for why this is a reasonable form for the scattered wave. This argument is not airtight because, in fact, in the real world, the scattered wave does not always have this asymptotic form. In fact, it turns out that in order to have this asymptotic form, the potential V has to die off rapidly enough. And I can't justify this at this point, but I'll tell you what the answer is. If you want to know how rapidly does it have to die off, the answer is it must die off more rapidly than the Coulomb potential. If you have the Coulomb potential, this doesn't work, and this is not the asymptotic form of the wave. The Coulomb potential has additional logarithmic phase shifts, which are appended to the e to the ikr, which are not trivial to understand. But if the potential dies off more rapidly than the Coulomb potential, then this is the correct form for the asymptotic form of the wave. All right. So what I'm going to do then is proceed by saying that the boundary conditions we want to impose on our positive energy solutions are captured by this, first of all, this decomposition of the exact solution into an incident wave and a scattered wave. Actually, this equation by itself doesn't have much content because it just defines a scattered wave. The content comes from demanding that the scattered wave have this asymptotic form, having basically outward going waves. You wouldn't want an e to the minus ikr because that would represent incoming waves and that would be non-physical. Okay, so there we are. There's the boundary conditions. Now then, this function f, which appears here as a complex function in general, and it's given a name, it's called the scattering amplitude. And people love to calculate the scattering amplitude because it bears a close relationship to the cross section, which is what I want to tell you about now. So let's go back to a drawing of our scattering situation here, X, Y, and Z. And let's suppose we've got some detector out here like so, some detector D like so, and I've got some direction out to the detector. And there's some solid angle, which I'll put around like here, some solid angle delta omega like this for particles that are going into the detector. Let's calculate the flux of particles going into the detector using the quantum expression for flux. So we do it like this. I'll remind you, there's a density rho, which is psi squared, and there's a flux J, which is the real part of psi star times minus IH bar gradient divided by the mass times psi. This is the probability density in current in a kinetic plus potential Schrodinger equation, which is what we're trying to solve now. Now, I have to say, however, the notion of probability density in current only applies for bound states, normalizable states, elements of Hilbert space, because a probability it has to be normalizable, or otherwise it's not a probability distribution. These states that we're dealing with are unbound states, and therefore rho is not normalizable, and therefore cannot be a probability density. Instead, we shift our physical interpretation for the purposes of scattering theory and this approach to scattering theory, and we interpret rho in effect as a density of particles in the beam. This is assumed to be a low density, so the beam particles don't interact with each other. And likewise, J then becomes the current of particles in the beam. So this is a slight change in interpretation of these quantities. All right, anyway, if we do this, then we actually have two currents. We have an incident current and we have a scattered current. Let's look at the incident current first. That comes from the incident wave, which is up on this last page. Here's the incident wave. Let me get this lined up so you can see it. The incident wave is just the incident plane wave, e to the ikx. So let's calculate what that current is. This becomes equal to e to the minus ik dot x. This the real part has to be out here to do it right. Times minus IH bar over the mass m times the gradient. By the way, this is the velocity operator you see in here. By the way, it's a velocity operator. Anyway, putting that in here, this operator here at times e to the plus ik dot x. And if you look at this, you see you don't actually need the real part. The gradient is easy to take. This just turns into h bar k vector divided by the mass m. But h bar k is, of course, the momentum divided by the mass m gives us the velocity. So this is the velocity. It's really the incident velocity of the particles in the incident beam. So that's the incident flux. All right. What about the scattered flux? So J scattered then, let's work this out. J scattered, well, we don't have a formula for the scattered wave everywhere. All we have for it is an asymptotic form at large distances. So the best that we can do for the scattered flux is to calculate not the exact scattered flux, but only its asymptotic form. So let me put a little tilde there. But this is going to be the real part of e to the minus ikr. By the way, this is k vector dot x vector in the incident plane wave. That's a plane wave. This is eikr. It's a magnitude of k times the magnitude of the radius, because that's a radial wave, spherical wave. I hope that's clear. I'm putting arrows in to try to dot products when indicated. All right, in any case, this is e to the ikr over r times f of theta comma phi complex conjugated. And then we have the gradient operator, which is minus IH bar gradient over mass m. And this is then applied to e to the plus IKR over r times f of theta comma phi, just to apply the formula for the current. Now this gradient will express this in spherical coordinates. The gradient in spherical coordinates is equal to r hat times the partial with respect to r, plus higher order terms. By that, what I mean is higher order terms, I mean plus terms that goes order 1 over r. Gradient operator, of course, has both radial and angular derivatives. And the angular derivatives, if you look at the formula, they all go like order 1 over r. So the dominant term is just the radial derivative. And so you can put that in here. You can take the radial derivative. You see you get two terms from the e to the ik dot r, and another one from the denominator, which will go like 1 over r squared. We throw away the r squared term because it goes to 0 as r goes to infinity more rapidly than the 1 over r term goes. And our tilde here says we're just going to get the leading asymptotic form. So that just taking the leading asymptotic form of this gradient acting on this wave function means neglecting the angular derivatives and also neglecting the 1 over r squared that comes from the radial derivative. anyway, when you put all that together, what you're going to find is that J scattered is equal to the unit vector in the radial direction, no surprise there, times the velocity v times the magnitude of f of theta and phi quantity squared, the scattering amplitude squared, divided by the radius r squared. You see, you got one factor of r here and another factor of r there. That gives us the r squared. In the denominator, there's an f star there and an f there. That gives us f squared. And this h bar k stuff over m gives us the velocity. And there's the r hat. That's where this came from. All right, in any case, this gives us the scattered flux. Okay, so we have both the incident flux here, right there, and we have the scattered flux for the positive energy solutions, scattering solutions we're interested in, with the boundary conditions that we're interested in. All right, now to go back to the picture of the detector here, let's calculate the rate at which particles are entering this detector. So that rate entering the detector, what is that equal to? That's equal to the scattered flux dotted into the area element of the detector, integrated over the aperture of the detector. That's what that is. But if I go back to my picture here, if I draw the distance to the detector, let me call that distance radius r like this, then the area element dA vector in the detector, this is outward pointing in like outward pointing from the origin, that's equal to r squared d omega times r hat, because it's the unit vectors in the radial direction. So plugging this in, then this becomes the integral over the aperture of J scattered, which is r hat v f squared over r squared, dotted into r hat times r squared times d omega, like so. This was r squared down here. And what you see is the r squareds cancel. The r hat dot r hat is equal to 1. The velocity comes out. The solid angle is a small angle, so in integral of the aperture, we just get delta omega. So this just turns into v times absolute value of f squared times delta omega. Okay, that's the counting rate. But this counting rate is also dw d omega times delta omega, where dw d omega is the differential counting rate. And dw omega in turn is related to the cross section in the following way, that this is equal to J incident times the differential cross section. Again, I'm defining the cross section as being the counting rate normalized by the incident flux. But the incident flux, this is just the magnitude of the incident flux. The incident flux as a vector was V incident. So its magnitude is just V. I'll just call it V. It's the same V as a scattered V. They're the same because of conservation of energy. And so this V then will cancel that V. The delta omega there cancels that delta omega. And we end up with a simple little formula that d sigma d omega is equal to the absolute value squared of scattering amplitude. And that was the point of this derivation, was to give you that. All right. So this is a neat and simple little result, but to recapitulate slightly, the scattering amplitude was introduced as the angular dependence of the outgoing spherical wave in the asymptotic region for the scattered wave. We're making no claims about what the scattered wave looks like at small distances where the potential is active, only at large distances where the potential has died off enough that we can actually talk about free particle solutions out there. Anyway, this was a definition of the scattering amplitude as a complex function of angles. But what we find then by doing all the fluxes is we find that the square of that f is the differential cross section. So people then like to calculate the scattering amplitude f, because once you square it, you get the differential cross section. All right, that's kind of the next phase, or the next block of material I wanted to cover tonight. So let me pause there and ask if there's any questions about this.
Just a small question. So when we're finding the incident flux and the scattered flux,
Yes.
then are we basically defining those two to be according to the equation, just plugging in psi as the incident psi versus the scattering psi, because we
Yes.
had earlier defined psi to be a sum of those two.
Yes.
So then there would be like cross terms and stuff. If
Yeah, yes, indeed, there are cross terms, and we'll worry about them later. For right now, allow me to dismiss them by saying our beam, let's say our beam has a finite width, and but the scattered wave then continues on out in a different direction. So if you move far enough out, you'll pick up just only scattered particles and not beam particles. I mean, in practice, this is how it works normally with scattering situations. But you're absolutely right. There are cross terms in there, and a careful analysis would take those into account. And we'll actually do that later on. This leads to the what's called the optical theorem. Those cross terms. Yeah, that's very observant of you to notice that. Are there any other questions? All right. If there's no other questions, I'm going to move on to the next major topic, which I will certainly not finish tonight. I hope I'll just get a start on it. The next major topic is going to be central force scattering. The central force scattering, better put it on screen here so you can see central force scattering. And the goal is just the same as what I was speaking of a moment ago. We want to solve the time independent, energy dependent Schrodinger equation for positive energy eigenfunctions with the right boundary conditions. That's the idea. But now what we will do is we will assume the potential V depends only on the radius R, which is to say that it's rotationally invariant. So we have a central force problem. Thus, we're going to be interested in positive energy solutions of a central force problem. Otherwise, the setup that I explained earlier about the decomposition of the wave into an incident plane wave and a scattered wave with the right asymptotic boundary conditions, that's all the same. That won't change. What is new is that since the potential depends only on the radius R, it means the Schrodinger equation is separable, as we know, and there's a radial Schrodinger equation for the radial wave function, and that can be solved, and then you end up with solutions that way. You can find solutions by separation of variables. In fact, we know that the exact solution, let me just write psi exact here, of X. Well, the exact solution is a linear combination of energy eigenfunctions. What do these energy eigenfunctions look like? I'll fill in some space here. What do they look like? Well, there's a radial wave function, depends on R of R, and then there's a YLN, theta and phi. The radial wave function satisfies the radial Schrodinger equation. I'll remind you what that is: h bar squared over 2m, 1 over r squared, ddr of r squared times d capital R dr, plus the centrifugal potential plus the true potential, which taken together form the effective potential times capital R of R, is equal to the energy times capital R of R. So this is the radial Schrodinger equation. You can't solve it unless you know what V is, of course. The radial Schrodinger equation is parameterized by the angular momentum quantum number capital L, and it's also parameterized by the energy. As I said, we're only interested in positive energies tonight, so that's understood here. But what that means is that the radial wave function is also parameterized by L, both by L and by E. There's no quantization in E. As continuous variable, it goes from 0 out to infinity because we're in the continuous spectrum. Now, it's customary in this business to parameterize the radial wave functions not by E, but rather by an equivalent wave number by writing E is equal to h bar squared k squared over 2m. That is to say, if it were a free particle, then k would be the magnitude of the wave vector corresponding to the energy E. And so for that reason, we'll write r sub k L like this, or let me write it here where I have a little more room, r sub k L of r. To be explicit about the radial wave function, it depends on k and L, and k is a parameter that indicates the energy. All right, so there's a solution of the of the three-dimensional Schrodinger equation for all positive values of K and all values of L equals 0, 1, 2, 3, and so on. They're all there. So the psi exact is going to be a linear combination of those. However, the Schrodinger equation that we want to solve is an energy eigenfunction equation. I wrote it down here a minute ago. It's just the usual Schrodinger equation, but I want to bring it back to emphasize the point I want to make. Here it is. Here it is. I can get these papers. It's just the usual Schrodinger equation, except for positive energy now. But the point is, we're interested in exact solutions psi, which are eigenfunctions of a definite positive energy. And so if we're going to represent those as linear combinations of these solutions from separation of variables, then the K parameter that appears there, which is related to the energy used in the radial Schrodinger equation, that energy must be the same as this energy. So what that means is that when we sum over solutions like this, the K value is fixed by the energy of the three-dimensional Schrodinger equation. So what we want is a linear combination that looks like this. We can sum on L and M, that's allowed, with coefficients I'll call ALM. But here the K is understood to be related to the energy by just a copy at h bar squared K squared over 2M. We block this off here. And that's where this K value is connected with. All right. So this is the exact solution can be written in this form. And of course, we get lots of different solutions for different coefficients A sub L. And what we want to do is to choose those coefficients, A sub LM, excuse me. We want to choose those coefficients so that the psi exact has the right boundary conditions. So to remind you, that means there's an incident plane wave plus the scattered wave that has the right boundary conditions. Let's talk about the incident plane wave. That's the next stage in this. In other words, I've got psi exact, you see, is equal to the incident plane wave. It's e to the ik dot x plus psi scattered. And I'm kind of running through these terms, I'm running through the three terms in this equation one at a time. Here's psi exact up here. Let's look at the incident plane wave now. Let's talk about that. So e to the ik dot x is obviously a solution of the free particle Schrodinger equation. However, we want the K here to be related to the K up there, which is related to the energy of the 3D Schrodinger equation we want to solve by requiring that the square of this K vector is the same as that K squared you see there. In other words, out in the asymptotic region where the particle is free, they've got to they all have to satisfy the same Schrodinger equation with the same energy. So let's just note that this K squared here is equal to K squared. It's the same K, in other words, except now here is a vector. All right. Now, we get the plane wave solutions if we separate the free particle Schrodinger equation in Cartesian coordinates. But you can also separate the free particle Schrodinger equation in spherical coordinates. And if you do, then you get a radial Schrodinger equation, and it has certain solutions, which are spherical Bessel functions. We talked about those last semester. So separating in spherical coordinates, what you get is solutions that look like this. You get the radial wave function is either J-type Bessel function of Kr, or a Y-type Bessel function of Kr. And then these are multiplied times the YLMs of theta and phi. These are the solutions in spherical coordinates. Let me remind you that the Y-type solutions are not allowed. They're normally excluded as free particle solutions because they diverge at the origin. They go like 1 over r to the L plus 1, whereas the J-type solutions are well behaved at the origin. Both these type solutions become oscillatory at large radii and just give you waves at oscillatory sines and cosines at large distances with a certain decay with distance. So if we're talking about a free particle that extends this free all the way down to the origin, then the J-type solutions are not allowed, and only excuse me, I didn't say it right. If we're talking about free particle solutions that can be extended all the way down to the origin, then the Y-type solutions are not allowed, and only the J-type solutions are there. So that means that that this e to the I k dot x can be represented as a linear combination of these J-type solutions. This is an expansion which, with enough effort, with special functions, you can work it out. And here's how it turns out to be. I'm just going to quote the answer. Is that this is a sum on L and M of 4 pi I to the L times J sub L of K, KR times YLM of R hat times a YLM complex conjugate of K hat. Now, what I mean by YLM of R hat is the same thing as YLM of theta and phi. This is just to say that there's this vector X you see over here, and it has a certain direction. And that direction has spherical angles theta and phi, or as a unit vector, I'll just call it R hat. Whichever way I write it, it's just a way of telling me the direction of the vector X. Likewise, this K hat here is the direction of the vector K. So there's a spherical angles in K space. You might call them alpha and beta if you want. And that's where this YLM is evaluated. In any case, this is the expansion, which I won't prove, but we will use, of a plane wave free particle solution. It's an exact expansion, plane wave free particle solution in terms of solutions obtained in spherical coordinates. All right. So I'm doing a digression now on the subject of free particle solutions. There's more that I want to say because I'm working on this now. The second term, we already did the exact term. Let's do the second term of this 3-term decomposition of the scattering wave. All right, so more about free particle solutions. If you want free particle solutions out in at large radii, like in the asymptotic region, that you're not interested in extending down to the origin, or maybe they can't be extended down to the origin because there's a potential down there, and so they're no longer free. But you want to talk about the solutions anyway, at large R, where they are free, then the Y-type solutions are allowed. Not only are they allowed, they're actually needed, necessary in order to get a complete set of solutions. So what that means is we do have to pay attention to the Y-type solutions as well as the J-type. We're going to need them both. And one of the things we'll need are the asymptotic forms of those solutions. So let me tell you about that. For the asymptotic forms, it's convenient to introduce linear combinations of the J and Y-type solutions that are called Hankel functions, spherical Hankel functions. They come in types 1 and 2, and they're called H stands for Hankel. They're indexed by the angular minimum quantum number L. And if I call the variable upon which they depend rho, like this, rho is usually identified with KR in the physical application. The definition is that H1 is equal to JL of rho plus I times YL of rho. And H2 is defined as JL of rho times minus IY L of rho. Now the J's and the L's are real functions. And so you can see the H1 and H2 are complex conjugates of each other. This is obviously like e to the plus and minus IKX that take you into sines and cosines. It's a similar idea. And so the Hankel functions are like complex versions. The Hankel functions are convenient for our purposes because they have nice asymptotic forms. As rho goes to infinity, the H1 of rho, L of rho, goes as, it goes as, I'll put equals here. It's equal this plus higher order corrections. It goes as I to the minus L plus 1, that's a phase factor, times e to the I rho over rho. And H2L of rho goes like goes like I to the plus L plus 1 times e to the minus I rho over rho. They're just complex conjugates of each other, as I mentioned earlier. You can see that from the definitions, but here the asymptotic forms are given, and those, of course, are also complex conjugates. So the I to the plus and minus L plus 1 is just a phase factor, and that has to do with the conventions that are used in the theory of Bessel functions. You just have to accept that. as far as the rest of it is concerned, what you can see is that the H1 represents an outgoing spherical wave because it's got e to the IKR in it, whereas the H2 is an incoming spherical wave that goes e to the minus IKR. You'll remember that our scattered wave doesn't have any incoming waves, it's only got outgoing waves, but they're both here with H1 and H2. All right. So using these asymptotic forms, if you want, you can solve for J and Y in terms of H1 and H2, and then plug in these asymptotic forms, and then you'll get asymptotic forms for the J's and the Y's. I'm not going to bother to do that because it's actually easier with the H's, but these are the asymptotic forms now. All right. I think that finishes all I want to say about the free particle solutions. And so the next step would be to go on to the exact wave and analyze that as well. But I'm out of time tonight, so I'm going to have to stop, and we'll pick up with this where we left off on Thursday. So that's all for tonight. Are there any questions about this? This is kind of incomplete so far on central force scattering, but are there any questions about it? All right, if there's no questions, then I'm going to turn off screen share.
Oh, actually, I was wondering, are there potentials, like scattering potentials that allow us, like in practice, that allow us to throw away the Y-type Bessel functions?
Well, the only potential that allows you to do that is a free particle. It's free everywhere, all the way down to R equals 0. Otherwise, you'll get the Y solutions that are out there.
Okay. Or is it possible that it modifies the Schrodinger equation, but it's still a Bessel function equation? Like,
well, if you're in love with Bessel functions, you might want to look for such a thing. I don't think so. I mean, the Bessel functions really emerge as, I mean, they really come from free particle solutions. That's what gives rise to Bessel functions. That's where that's where they're born, you know.
mm-hmm.
There may be some way of doing what you're asking, but I don't know how to do it.
But then if there's no, if it's just a free particle, that then I guess there's no scattering psi then.
Well, if there's no Y function, then you're just talking about the J functions, and that is a free particle. So there's no scattering. No.
I mean, in that case, in that case, the exact psi would just be the original e to the ik dot x, right?
Yeah, if there were no potential, you just have the incident wave. There would be no scattered wave.
Right. Okay.
Yeah. All right. Any other questions? All right. If not, we'll call it an evening. I got through about 1/3 as much material as I wanted to tonight, but that's how it goes sometimes. Probably means I needed to take time to do that stuff. Now, if I can find the little arrow in my computer here, where did it go? Here it is. All right. Stop screen share. And I shall stop recording.